Year 12. Bonjour. Right, it's been a few weeks since I've done one of these videos because unfortunately I did lose my voice and I didn't want to sound like a frog. It's just come back, so let's do it. Right, Key Area 3, coasts. We kick off with how changes in sea level influence the coastline. Alright, so first of all we need to understand the different ways sea level can change, and I'm sure that one or two of these ways might surprise you a little bit, so it might debunk, what a word that is, debunk, it might debunk some of your perceptions on what causes sea levels to change and the different types of sea level change. Yeah, and you know, we think of sea levels changing probably currently like contemporary sea level change, so what's been happening in the last 10 years, 20 years, 30 years, 50 years, 100 years due to global warming and the melting of the ice caps, for instance, which I'm sure you've probably done at primary school. But I think context is very important for geographers, and you know, we're aware of scale, but we're also aware of time scales as well. And sea levels have been changing and fluctuating for hundreds of thousands of years. So we've got to kind of put things in context a little bit. Yeah, so we're going to get a really good understanding of what causes sea levels to change and how that then affects what landforms we see. All right. Right, I'm going to kick off with a couple of key words. So give it a title, nice shiny new page. How does changing sea levels influence grammar? How does changing sea levels influence coastlines over different time scales? All right. The first pair of keywords we're going to distinguish between is one is marine regression. So write that, marine regression. Marine regression just means where the sea level drops and produces an emergent coast. So if we think back to first or second lesson with me, we looked at Valentin's model, and there were 4 quadrants, if you like, on that model. One was an eroding coastline, which would be retreating. One quadrant represented the depositional coastline, which would be advancing, and then there were 2 which probably fried your brain a little bit. One was a submergent coast and one was an emergent coast. Alright, so think emerging, land is popping up out of the water. Submergent is it's being drowned. So marine regression is where the sea level drops and produces an emergent coast. So land is being created. Yep. Marine transgression is the opposite. So it's where the coastline is flooded and produces a submergent coast. And this is very important because whether we get an emergent coast or a submergent coast affects the type of landforms. Alright. Right then, eustatic change, the next keyword. Eustatic change is the change in volume of water in the oceans. Please don't assume that means that it's always rising, because sea levels can actually fall as well. Yeah. So the definition of eustatic change is a change in the volume of water in the oceans. We can have more water in the oceans, or we can get increasingly less water in the oceans, which might fry your brain a little bit. Make a little note of this: eustatic change is always global. Alright, so currently the sea levels are rising eustatically. Right, ice caps are melting, and that water is then running into the oceans, and we've got more volume of water in the oceans. That change is consistent right across the planet. All right. So imagine if you're running a bath. You're running a bath, and you're putting more and more water into that bath. You know, and if I said to you, well, how does the water level rise? It obviously rises the same whether you sat at the front of the bath, the back of the bath, or in the middle of the bath. Yep. You put more volume of water in, the sea levels rise consistently. Yeah. Isostatic change is when the land height changes in relation to the sea level. So land can either spring up or it can subside down. Yep. So you can see it's getting a bit confusing, it's getting a bit more complicated. We can have more or less water in the oceans, but we can also have land and continents rising or falling. And it's a combination of eustatic and isostatic change which determines whether we've got marine regression or marine transgression. Right then, next slide, here we go. Couple of keywords. I've been a bit lazy, I've nicked these off interweb. It does the job though. So yeah, eustatic change, global scale sea level change caused by a change in volume of water in the ocean. Always global. You put more water into the oceans, the whole of the oceans across the planet rise, don't they? Isostatic change, it's local. So in some places the land height is rising relative to the level of the sea, but in other places it's subsiding relative to the level of the sea. And I'll just pull a little example here for the UK, which is interesting. And what this shows is the different figures basically tell us whether the land is rising or falling and by how much. So if we look at the red figures in Scotland, 1.5, this will be millimetres per year. So Scotland is rising isostatically. The land is springing up at 1.5 millimetres per year. All right. In the southeast, like Kent, Thames estuary, the land height is sinking, or subsiding. So by about 0.7 millimetres per year. So we've got this kind of local difference, where part of the northern part of the UK is rising upwards, and the southern part, southeast of the UK, south of the UK, is subsiding downwards. All right. Eustatic change is always global. You rub more water into the oceans, then the sea levels increase. Whereas isostatic change is local, just like we've just seen. If land is emerging, then obviously we've got marine regression, the sea is in effect going backwards. If land is submerging, then the relative sea level is rising and we've got marine transgression. So you might want to pause it, play it back, make a few notes, get your head around this, because it can sort of fry your brain, because you've got to debunk some of the assumptions that you've probably had for a long time, since you were nippers. Okie pokey. Right then, so what causes eustatic sea level change? Keep it nice and simple. If I went to my mum, or if I went to a year 5 kid in a primary school and I said, "Oh, you, what causes sea levels to rise?" They're going to spout something. They're going to say something like, well, ice melts. And they're kind of right. I guess they're on like lines. We need to be a bit more specific than that, a bit more accurate and precise. That's the buzz phrases for this month. Accurate, precise use of terminology. So what causes eustatic sea level change globally? Right. There's a list just here on the right hand side. The main one, the most significant one, at 1.38 millimetres a year, is called thermal expansion. So that is the most significant cause of eustatic sea level rise. Thermal expansion of the oceans. Yeah, you need to write that. What is it? Well, the more the oceans warm up due to enhanced global warming, so we can sequence it through, we get enhanced global warming, the oceans warm up, and the water particles have got more energy, so they vibrate more. And because of that, they expand. And put this in brackets, or because the water particles expand, it kind of swells the oceans up ever so slightly. It doesn't take much for it to have an effect. So the oceans swell. That means there's more volume of water in the oceans, which is, by very definition, the definition of eustatic sea level change. More volume of water in the oceans. The last stage, sea levels rise. Yep, and this is the most significant, 1.38 millimeters per year. Doesn't sound like much, but 10 years later, you're going to be at what? Nearly 1.4 centimeters. In 100 years, you're going to be at 14 centimeters, right? So it seems to be happening slowly, but it's still having an impact. The second cause of eustatic sea level change that we're seeing at the minute is ice caps melting, all right, or ice sheets, glaciers melting, all right. The most significant one is the Greenland ice sheet, and if you just look at this map, you can see white is a permanent ice sheet, orange is the ice sheet that melts in summer, and green is seasonal ice coverage. So you can see, that ice sheet is shrinking, it's getting smaller, it's melting. That's what that map is showing you. From 1992 to 2007, it's getting smaller. Therefore, what's going to happen? The land ice that you see here melts, it flows into the oceans and causes eustatic sea level rise. Glaciers melting as well in alpine environments. That water, under the force of gravity, flows into rivers and then flows into the oceans. So the second cause is ice cap and glacier melt. Yep, you've got a couple of examples here. The Greenland ice sheet is a big one. You've got Antarctic ice sheet, and then you've got your alpine glaciers. Yep, and this is their significance. I think last lesson I introduced this idea of geographers. We don't just explain things, but we need to make judgments and assess what factors are more significant. We've got to make judgments. So in this case, the most significant factor that causes sea level rise eustatically is thermal expansion, and then your ice caps and your ice sheets melting. Your glacier one is the third most significant. Okie pokey. Right then, isostatic change, remember, is where the land height is either rising or falling, and it's local. The land in Scotland is rising, the land in the southeast of the UK is subsiding. So this, depending on the place, different processes are in operation in different places, and some coastlines are falling, some coastlines are rising. Yep, so what causes this then? Well, we're going to watch some videos in lessons, so I'm just going to introduce them. I'm not going to get into the nitty gritty. First one is, let's have a look, is land ice. All right, and if we have let's get rid of all these so you're not distracted. Right, I just want you to focus on this top. In fact, watch this. Come on, give me a shape. Right. Normally, continental crust floats on the asthenosphere, just the upper part of the Earth's mantle, right? And it's in balance, stays quite stable, it's in equilibrium, right? During the last ice age, ice sheets, some of them are kilometres thick. They take thousands of years to kind of build. The temperature drops, and gradually there's more snow on land, falling on land. That compacts into ice. Tens of thousands of years, we get glaciers and ice sheets that are kilometres thick. They obviously weigh millions and millions of tons. So what happens is the weight from the ice cap, or continental glacier, or land ice, you must use one of those terms, the land ice, the weight of it, causes the continental crust underneath it to sink into the asthenosphere. Alright, so it sinks, the weight pushes it down. Yeah. At the end of the last ice age, I think roughly about 10,000 years ago, roughly, at the end of the last ice age, when the ice melts and the weight's removed, physics tells you that if you push down on a spring, like in this example, it's going to, and you remove that force, it's then going to spring back up. So when the continental glaciers and ice caps melt, the removal of the weight of ice allows the continental crust to isostatically rebound upwards. And if we just have a quick nosy at Scotland, wee bonny Scotland, if we just have a look at Scotland, yep, that's why Scotland is rebounding isostatically, because obviously Scotland's further north, and during the last ice age it received more weight pushing down on it from thicker ice sheets. Yep. So when that weight's removed, Scotland is now very slowly adjusting, and it's isostatically rebounding. Yep. It's adjusting and springing upwards. All right. Whereas the south didn't receive really thick glaciers or ice sheets, so the weight of Scotland springing back up is called a seesaw effect, and that's causing the southeast to now subside. All right. So yeah, what causes isostatic sea level change locally? One of them is, well, land ice. Yep, ice on the land. And when that melts, we get isostatic rebound. Right, the second one is tectonic activity. So we do study the tectonics topic after Christmas. I'll kick off with coast first. Right, so this will probably make more sense when we study it in tectonics. But if you've done it at school, then basically we can get tectonic pressure from tectonic plates converging together, and that can push or fold. We've done a little bit on folding actually. It can fold and push rocks upward, or strata upward, and it can uplift them. Yep. So if you think of the land in relation to the sea, if you've got this process happening and tectonic pressure is pushing and folding strata upwards, you've got an emergent coastline, haven't you? Again, it is local. It's going to be in some places it's going to happen, in others it's not. Yeah. An example of tectonic uplift, just here, Turricarrai Head in New Zealand, and you can see these kind of markers, if you like tide marks on the land, where it's evidence of where the sea level was in the past. So this is where the sea level is currently. You can see it. But if you went back to 1855, this would be the sea level. 2,300 years ago, when Jesus was a small boy, then yeah, your sea level would be much higher. So this land is emerging, all right, isostatically upwards. It's rising. We're gaining more land. Yep. So that is an example of marine regression, because we've got an emergent coast. The land is rising upwards. So tectonic uplift is your second cause. The third cause is sediment accretion. So sediment, sand, silt, mud, clay. Accretion, it builds up. Typically, in river deltas and in estuaries possibly, and the weight of that sediment has a similar kind of effect to the glacier ice, but it's not significant. So obviously, just in this photograph, you've probably got tens of thousands of tons of sediment that can push down on the continental crust and cause isostatic subsidence in that locality. It's only going to happen in this local area. Yep, nowhere near as significant as the glacier. Yep, because there's not as much weight. Okay then. So, how does this affect what we see? All this is the kind of theory, and we can get really deep into it and in a bit of a tangle. Isostatic, eustatic, regression, transgression. Let's just keep one eye on kind of why we're studying this. Why is it relevant to coast topic? Well, it affects the landforms and features that we see. And I'm not going to spoil the surprise. I want you to have a think. I'm not going to explain all these because I'll do that in lesson. But you have a think. We've got a fjord, a ria, a series of raised beaches, and what we call a fossil cliff. Alright? You can do a bit of research, or you can just have a look at the photographs, up to you. What type of sea level change causes each one of these? So please do this activity and have a think. I'm going to be asking people to start next lesson. Don't just think, he's not told us answer, so he can't check his notes. Yeah, just have a think. Is it, first of all, for each picture, is it marine transgression or marine regression? So you've got to make a judgment. Is it caused by sea levels dropping, which is marine regression, or is it caused by marine transgression and flooded coastlines? And then think which type of sea level change has caused each one. So it can either be isostatic change or it can be eustatic change. Yeah? And have a think. Have a look at the landforms and the features and see what you come up with. Okie pokey. As it was with everything. Yep. Keep it neat and tidy. Titles, subheadings. Use different colours if you want. Keep your notes neat. Keep tidy. Keep pride in what you do. And I'll see you Thursday. Okie dokie.